Ribosome A site, the base pairing is strengthened by additional hydrogen bonding with the ribosome. Incorrectly bound tRNAs do not base pair as strongly with the ribosome. In prokaryotes, after an initiation complex is formed, elongation occurs. During elongation, the ribosome synthesizes proteins by linking together amino acids. 3 steps are needed to add each amino acid. A charged tRNA is placed in the A site of the ribosome. A peptide bond is formed, and the tRNA with the growing protein chain is moved from the A site to the P site. In prokaryotes, this requires 2 translation elongation factors, EFTU and EFG. A third elongation factor, EFTS, is needed to recycle EFTU. Elongation is very similar in eukaryotes, and only the prokaryotic process will be described here. When the triplet anticodon of the correct tRNA is base paired with the mRNA in the ribosome A site, the base pairing is strengthened by additional hydrogen bonding with the ribosome. Incorrectly bound tRNAs do not base pair as strongly with the ribosome and are released before they can be added to the growing polypeptide chain. Correctly base paired tRNAs have additional hydrogen bonds that help the tRNA remain in the A site during accommodation, the process whereby the tRNA rotates into position for peptide bond formation. First, a charged tRNA is bound by EFTU and is brought to the ribosome A site as an EFTU GTP amino acyl tRNA complex. The tRNA anticodon binds the mRNA codon, and EFTU hydrolyzes its GTP, and the resulting EFTU GDP is released from the tRNA. Next, a peptide bond is formed between the amino acids. This reaction transfers the amino acid from the tRNA in the P site onto the amino acyl tRNA in the A site. To prepare for addition of the next amino acid, the ribosome undergoes translocation, a process in which the ribosome moves along the mRNA to the next codon. Translocation is facilitated by elongation factor EFG. The tRNA with the growing amino acid chain attached moves from the A site into the P site, and the spent tRNA in the P site moves into the E site. Note that elongation factors EFTU and EFG both end up as complexes with GDP after one round of elongation. Both factors must exchange their GDP for GTP before they can be used again. For EFTU, this exchange is facilitated by elongation factor EFTS. For EFG, the GDP simply falls off and is quickly replaced by a GTP. The process continues. At each codon, the corresponding amino acyl tRNA binds in the A site. The growing peptide chain attaches to the amino acid on the tRNA in the A site, and the ribosome translocates, moving the growing protein chain and tRNA into the P site, and freeing up the A site for another round of amino acid addition. Termination of translation is engaged when a stop codon on the mRNA enters the A site of the ribosome and is performed by release factors that recognize the stop codon. The mechanism of termination is similar in prokaryotes and eukaryotes and involves 2 kinds of release factors called class 1 release factors and class 2 release factors. Class 1 release factors enter the ribosome A site and bind the stop codon using a peptide anticodon. Prokaryotes have 2 class 1 release factors, RF1 and RF2. Eukaryotes have 1 class 1 release factor, ERF1. The class 2 release factor, in complex with GDP, also binds the large subunit. In prokaryotes, RF3 is the class 2 release factor. In eukaryotes, ERF3 is the class 2 release factor. After the class 1 and class 2 release factors are both bound, a glycine-glycine glutamine, or GGQ motif, on the class 1 release factor triggers hydrolysis of the protein from the tRNA in the P site. Release of the protein from the ribosome triggers the recycling of the release factors. First, GTP is exchanged for GDP on the class 2 release factor. This causes the class 2 release factor to push the class 1 release factor off the ribosome. The release of the class 1 release factor allows RF3 to interact with the factor binding center, which stimulates RF3's GTPase activity. GTP is then hydrolyzed on the class 2 release factor. The class 2 release factor GDP complex then releases from the used ribosome. At this point, the ribosome still contains 2 deacetylated tRNAs and is also still bound to the mRNA. The process of cleaning out the ribosome and separating the subunits is called ribosome recycling. Although not as well understood in eukaryotes, in prokaryotes, this process involves a ribosome recycling factor plus initiation factor IF3 and elongation factor EFG. The ribosome recycling factor, RRF, binds to the A site of the used ribosome and recruits EFG to the complex. The RRF acts like an A site tRNA during the translocation process. EFG can thus push on the RRF in the same way as it would on a tRNA. This moves the RRF into the P site and releases the 2 spent tRNAs. Next, both the RRF and EFG uncouple from the ribosome. The mRNA is released, possibly with the aid of IF3. IF3 binds the small subunit to prepare it for another round of protein synthesis. Many antibiotics work by selectively targeting the bacterial ribosome, blocking translation. Because these medicines are unable to bind eukaryotic ribosomes, antibiotics are deadly to bacteria, but non-toxic to people or animals. Watch the effect of each antibiotic on the prokaryotic translation process, then decide what part of translation is derailed by the action of the antibiotic.